All right, here we go. So, skier. So here's the deal. We've got this. We know the mass of the person. We know the angle of the slope. They give us the coefficient of kinetic friction between the skis and the snow. So after starting from rest and skiing 16.5 meters downhill, the skier enters an area of wet snow, and the coefficient of kinetic friction increases, making the net force on the skier 0. Okay, so let's think about this situation. Skier starts off on the slippery snow and accelerates, right? Because there's not very much friction. So there's some net force pushing him down the hill, right? You hit the wet snow and what happens? Well, okay, not necessarily slows down, but if the net force goes to 0, what does that mean?
It's not accelerating.
No longer accelerating, right? So now the little bit stickier snow just causes the person to maintain that speed and not accelerate anymore, right? Make sense? Okay. So we really got two parts to this, don't we? First part says the skier is moving at a speed of blank when she enters the wet snow. So that's just a part A problem, isn't it? Right? And it looks like maybe that's going to be a kinematics problem, right? So for part A, when you're skiing on the slippery snow, let's think about this from a kinematics perspective. What do we know for part A? What information is given to us? The initial speed is what? 0. Okay, so we know initial velocity is 0, right? That we know the displacement, don't we? Yeah, the displacement, delta D is positive 16.5, and we're looking for final velocity, but that's all we have, isn't it? What do we probably need? Yeah, if we had acceleration, right? If we could fill in the blank with acceleration, then we could answer the question, V final equals what? And that'd be pretty easy to do. We could just use the bottom equation, right? Without time. Agreed? Okay, so, but let's think about this now from our, we've added a bunch of stuff since we did kinematics, right? To find acceleration, that's a force issue, isn't it? Right? So how are we going to go about finding what the acceleration is during part 1? What are we going to have to do? Now it really just comes from Newton's second law, right? Net force equals ma. Agreed? Okay, so yeah, so this is a whole force issue that we need a free body diagram, right? Equations of motion that we can use to solve for A, right? So let's go to part A, and we're going to need a picture, right? So we're going down the hill. So how's this? This will be our picture. Okay, so there's our slope. Agreed? Okay, what's the angle? 23.2. Okay, everybody with me? So then we're not going to draw anything complicated. We're just going to use a dot for our person. And what are the forces acting on the person? Before we do that, what's going to be the reference frame we want to choose? Probably not X and Y. What are our directions going to be in this case? Parallel and perpendicular, right? Because the motion is parallel to the surface, right? So it'd be really complicated for us to try to make this an X and Y problem, right? Because none of the motion is in the X or the Y direction. So we're going to set up the reference frame where we consider that to be the positive perpendicular direction, and we'll call that the positive parallel direction, right? Everybody with me? Okay, and then how about, here, let me redraw that though. It's not a very convenient spot. So here's our key, right? Whoops. Here's our key right here. We're calling that the positive perpendicular direction, and we're calling that the positive parallel direction, right? Okay, so what are the forces that are acting then? We'll start with just remember how we do this now. This is this is a big process solving a problem like this, right? We're going to start off with just all the forces just pointing in the directions that they actually point, and then we're going to break those into the components, right, along our chosen directions. So what forces act? Gravity. So we know gravity acts. So one force is just going to be mg, right? Okay, good. What else? Friction. In what direction is friction going to act? Okay, it's going to be against the motion, right? So it's going to be kind of uphill in this case. So there's our kinetic frictional force. Okay, what else? Normal force, yeah. And in what direction is normal force going to act? Perpendicular to the surface. Okay, so there's normal force. And that's it, right? Everybody agree? That's it? So what's the force that's making us go down the slope? Duh. Gravity. Yeah, there's going to be some component of gravity, right? So we've got to take this picture then, and 2 for 3 ain't bad, right? 2 of the 3 forces are pointing in the good directions for us, but we've got to break gravity up into parallel and perpendicular components, right? Okay, so let's do that. So gravity then, we're going to take this and we're going to break it up into a parallel or a perpendicular component and a parallel component that we're going to trade for the whole thing, right? So if this is 23.2, let's just call it theta, because it's hard for me to write something that small up here. Which of these angles is going to be theta? That one or that one? Top one will be, sure. Okay, so if that's theta, now we should be able to write out those components, right? So what's going to be the perpendicular component? That's just going to be the whole thing, you know, mg. We're always going to, remember, when we write components, we're always just multiplying the original vector times either sine or cosine, right? So do we multiply by sine or cosine for this guy? Cosine, yeah, because that's going to be the adjacent side to that angle, isn't it? Right, so that component is mg cosine theta, and then this one down here would just be mg sine theta, right? Everybody agree? Okay, and so now what we could do is we could write out our orthogonalized free body diagram, and that's going to look simpler, right? That's just going to look like here's our point, let's say, and if we add up all the forces that are acting in the various, you know, in the parallel and perpendicular directions, well, the normal force looks the same, right? And friction looks the same. But now we'll just take these other vectors and we'll just translate them to the right places. We'll slide them so they, right? Because when we draw a free body diagram, we want all the forces starting at the object, or if there are multiple forces adding in the same direction, let's add them tip to tail, right? So this guy looks good. He's in the right spot. There's our mg cosine theta, but we got to take this guy and slide him up to there. So there's our free body diagram, right? So now let's make equations of motion out of that. What's that tell us? So we should be able to take the 2 different directions that we chose. We've got the perpendicular direction and the parallel direction. So in the perpendicular direction, let's add up the positive and negative forces. Okay, Abby, what's a positive force acting in the perpendicular direction? In that free body diagram. So remember, here's our perpendicular direction is the one that's pointing perpendicular to the surface, so it's the one pointing that direction. So normal force, good. So we're going to end up with equation 1, we'll call this. We've got normal force. What's going to be a negative force or component of a force acting in the perpendicular direction?
Oh, the coefficient of mg cosine.
Yeah, mg cosine theta, right? Everybody see that? That's the one that's pointing down perpendicular to the surface in the negative direction.
Oh, that minus I equals 0.
Okay, what's gonna be the acceleration that's acting perpendicular to the surface? Zero. Yeah, it's not accelerating into the surface, right? So that equals 0. Okay, and just to remind us what this all is, this part right here, what you really just did is you just added up the perpendicular component of the net force, right? Right? Net force is just the sum of all the forces acting. So in that direction, there were only 2 of them, right? Okay, there's one equation of motion. Now let's go down and create the equation of motion. We'll just call it equation 2. Let's look at the net force acting in the parallel direction. So what's the positive component there, as we've defined it? mg sine theta. Okay, what's the negative component? Frictional force. Good. So minus kinetic friction equals, and now we should expect some acceleration there, right? So that's ma. Okay, good. And let's remind ourselves where all this came from. This stuff right there, we really just added up the parallel component of the net force, right? All the parallel forces. So those are our 2 equations of motion, and really all the physics that we did was just essentially to build that system of equations, and now we'll just solve that, right? We got to remind ourselves what friction is, true. So what's our friction model? What is kinetic frictional force?
It's
Good. Use of K, so the coefficient times normal force. But we know from this first equation up here, don't we? That really is just telling us that normal force equals mg cosine theta, right? Everybody agree? So then we could turn that into kinetic frictional force equals mu mg cosine theta, right? And so then that second equation down here becomes more useful. Now that second equation is just going to become mg sine theta minus frictional force, but there's my frictional force right there, equals ma. Okay? Does it depend on the mass of the skier? What happens to that equation? What could I do to the m's? They cancel out, don't they? So that's the physics gods telling us it doesn't matter what your mass is. The problem's the same for anybody, right? So we could divide both sides by m and get rid of all the masses, and there's acceleration. All I got to do is plug in that information, and it's going to give me acceleration, right? So let's see what we get. Acceleration then equals g. So 9.80 sine, what was it, 22.3? Yep, or 23.2. Minus mu, which was 0.111. Times g times cosine 23.2 degrees. That's just calculator stuff, right? So that's giving us acceleration. So let's plug that in, see what we get. So if I plug all that in, 9.8 times sine 23.2 minus 0.111 times 9.8 times cosine 23.2 gives us that 2.86 blah blah blah. That's my calculator number for acceleration, right? Make sure, am I in degrees? Yes, I am. Okay? So now we can just really go back to the kinematics problem, right? All that hard physics we did was really just to get acceleration. And now we go back up here and we fill in the blank. Acceleration is, what was it? So it's roughly 2.86. We'll keep the number on our calculator though, right? And we can solve for our final velocity now using that bottom equation, right? So really, I could just take this information here. That's all we really need for this problem. It's just that stuff. Go to the next page. Oops. Oh no. There we go. What? What do I do? There it is. So there's everything we needed. The equation is just going to be this guy, right? So V, we can use V squared minus V naught squared equals 2A delta D. V naught is 0, so V squared equals 2 times A, which is in our calculator, times 16.5, and V would just be the square root of all that stuff, right? So what's that give us? So we get square root 2 times that number times 16.5 is that, 9.72 meters per second. Okay, so that's the answer to part A. Okay, and then what else did it want? The coefficient of friction between the skis and the new wet snow. Okay, so that's no big deal. Really, we've done most of the hard work for this. How is that going to change our equations of motion for part 2? Does it change the first equation? No, it doesn't, right? Our equation of motion still looks like this, doesn't it? Still looks the same. Only difference is now the friction's just gotten a little bit bigger, right? That's it. So that's still the equation perpendicularly speaking. What about the parallel equation? If the net force is 0, yeah, it's just equal to 0, right? It's the same equation as before. The only difference is now acceleration is 0, so it's just equal to 0, right?
So mg sine theta is equal to the coefficient.
Yeah, exactly. So down here then, we just end up with this whole thing equals 0, right? And we're just solving for mu, aren't we? Right? Does that make sense? That's the only unknown. So what would that become then? We just end up with g sine theta, if I just add this term to the other side, equals mu g cosine theta. Remember, the m's canceled. It still cancel.
So
And so mu just equals the ratio. It just equals,
that's what we're looking for.
yeah, so mu, right, is going to equal g sine theta divided by g cosine theta.
But can you just cross out the g's?
Yeah, we can.
So it's just sine theta divided by cosine theta.
So it's just a tangent of theta. How about that? It's mu in this case.
Oh, so you can just put tangent and then your
Yep.
easy.
That's it? Okay? Make sense? Okay? All right, so there's that guy. How about, let's take a quick look at, you pick one on 7.2. So we did, and I've already put up videos for, it looks like, problems 2 and 3. Right, so let's look at these other ones. What's 4? Okay, player kicks football from ground level at this angle within a certain initial speed. We want to know hang time and maximum height and distance of travel. So we could look at that one. Or we could look at, this is a good one. Stones launched at an unknown angle and you gotta find the angle. Yeah.
Use on what hang time and stuff.
Hang time?
How long
Okay.
it's in the air?
But
Yeah,
we
just,
can-
right, how long it's in the air, right. So let's go back and just
Oh,
talk
so
about,
that's just like finding time.
yeah.
Oh,
Mhm.
that's easy.
Yeah, this one really, we don't probably have to do the whole thing, let's just talk about how we could do this, right? So this is gonna be a parabolic trajectory, right? The ball's gonna go up in the air, get some maximum height, and then come back down. But we could take, this is, vertically speaking, this is the same problem that we dealt with last chapter when we threw a baseball up in the air and caught it, and we asked how high did it go, right? So if we can just figure out what the initial vertical component of the velocity is, right? It's the very same question as we had last time where we throw the ball up with a certain speed and then we want to know how long it's in the air. Well, remember the trick we used for that is we said the motion is going to be in two parts. The journey up is the same as the journey down, right? And so we could say, okay, well, let's just figure out how long it takes for the vertical velocity to come to zero, right? Till the ball reaches its maximum height vertically, and then find out what that time is. And that's gonna be half of the time that it's in the air. It took half the time to go up, and it'll take half the time to come down, right? Does that make sense? And so then by asking for that time, if we just take this kinematically and say, okay, how long does it take for the vertical velocity to be zero?
That's hang time.
That's half of the hang time, isn't it? Right? That's half of hang time. How long does it travel? Well, we'll just figure out whatever the horizontal velocity is. Whatever the horizontal component of velocity is times the hang time is how far it goes horizontally, right? And then how high does it go? Well, it'd just be like asking, how high did that ball go, right? What's its displacement gonna be when the velocity is zero, right? Does that make sense? Okay, so really, we'll just set this up and you guys can do all the work, but if this is the information that we have, 46.2, wouldn't you agree that if I were to draw, if this is the initial velocity vector, that's 46.2 degrees and the velocity has a magnitude of 30.4, then what's going to be the vertical component? We could call it V naught sub y. What's that going to be in terms of that angle in our initial velocity? It's going to be a sign issue, isn't it? It's going to be an opposite, isn't it? Right? So it would just be 30.4 sine 46.2, just some number. And the horizontal component is going to be constant. I just call it v sub x, right? Because horizontally, we know for projectile motion, the velocity stays the same horizontally the whole time. So the initial velocity and the final velocity horizontally is just going to be 30.4 cosine 46.2, right? And then all we'd have to do is just make, all we'd have to do here then is say, okay, so vertically and horizontally, just make two columns. And so V naught sub y equals whatever that was, 30.4 sine, what was it again? You remember 30.4 sine something? 30.4 sine 46.2. Okay, horizontally, v sub x is 30.4 cosine 46.2. So vertically, why don't we just ask the question, when does v sub y equal 0, right? Does that make sense? Okay, that's going to be at the top, right? What's the acceleration that's happening vertically to the ball?
30.
The acceleration.
Right.
Just gravity, isn't it? Right. So a sub y is just negative 9.80, right? And we're just looking for maybe time, right? And maybe displacement. So if we knew what time was, I'm going to call that t sub 1/2 because it's really the time for half of the flight, isn't it? The time to get to the top. We could solve for that using equation 2, right? Right? And if I want to know how high it went, I could solve for that using equation 4. I could fill in those blanks, and that answers 2 of my questions, right? Everybody agree? And then over here, whatever I get for this, I fill in over here, right? So t sub 1/2 equals whatever answer we got there goes there. So the total hang time just equals 2 times the time it took to get to the top, right? And if I want to find how far it traveled horizontally, that's just an equation 1 problem, right? Make sense? Okay. So you guys can fill in that blanks. I mean, really, all we had to do, the only part that's any different here is just calculating what the initial horizontal and vertical velocities are, and then we just break it into these separate columns, deal with them independently.
Can I put t 1/2?
Well, okay, so this is what we call the time it took to get to the top, right? Because when is the vertical velocity 0? Vertical velocity is 0 when the ball's up at the very top, right? Still gotta come down. So we just found the time for half of the flight to get to the peak.
So then you just have to multiply by 2.
Multiply it by 2 to get the whole time, right? Okay? Questions on that? So you guys could just take that one from there. Let's maybe look at that last one. That one that one is kind of tricky. We'll do that one. And I know I didn't make it worth a ton of points because it is pretty tricky. So it's worth 6 points, yeah. So you could get a 94% without even getting this one. But I want you to, I mean, you should try it. It's a good one. So what do we know here? We're launching with this speed, right? The displacement is going to be, vertically is going to be what? If that's the cliff.
Negative 90.
So it's going to drop by 90.9. So the vertical displacement is negative 90.9. And it tells us the time, right? And it just wants to know what's the initial angle and how far from the base of the cliff does it hit and what's its speed going to be, right? Okay, so then write those numbers down because I'll forget them. 16.5, 90.9. Was it 6.11 seconds? Was that time? I think. Yeah, and 90.9. And okay, agreed? And this time we don't know the angle. So if that's our initial velocity, we're just going to call that theta, right? So what's our initial vertical component of velocity going to be then? What are we going to get? What's the initial vertical component going to be? We have to just write it in terms of theta, because we don't know what theta is. right? So in the y direction, if we break this into columns, in the y direction, v naught sub y is just gonna be that, right? And that's gonna be a cosine, or a sine, 16.5 sine theta. We don't know theta though, right? What we said that vertical displacement is negative 90.9. We know t, 6.11, and we know acceleration, right? Okay. How could we set up an equation here to solve for what theta is then? Can we think of an equation that relates all those things?
Number two.
Not two, because we don't have final velocity.
Number
Number three, right? That guy. So the equation we can use, if we write it in terms of y's, would just be displacement equals v naught sub y t plus 1/2 a sub y t squared, right? What's that become? Negative 90.9 equals 16.5 cosine theta times t minus 4.9 t squared. What's the only unknown in that equation? Whoops, no, we know t, don't we? I can plug in values for t. Times 6.11 plus 1/2 times negative 9.8 is minus 4.9 times t squared. So what's the only unknown? Theta, yeah. Right, so I should be able to actually solve that for theta. What would I do to get the theta by itself? Eventually, right? But first I've got to get the cosine by itself, right? And this is, I mean, that's why this is a bonus one. It's kind of tough. I'd have to get the cosine by itself and then just take an arc cosine, right? So I got to get this term by itself, so I'd add this term to the other side, right? So I'd get 4.9 times 6.11 squared, whatever that is, add that to that side, minus 90.9 equals that term, 16.5 times cosine theta times 6.11, right? So I could divide each side through by 16.5 times 6.11. And those cancel, so I just got a cosine theta, right? So cosine theta just equals whatever my calculator tells me that number is, right? So what's theta? How do I undo a cosine theta, remember?
Oh,
Arc cosine, right? So then if we get the equation, cosine theta equals that, would have been easier just to leave these in terms of like t's and delta y's, right? And then plug stuff in at the end. That's what I should have done, really. I put the numbers in. So I just got some big number there, and then I'm just gonna take the arc cosine of both sides, right? See what my calculator gives me. And that's the answer. And once I get that, from there it's no big deal, right? It's really no big deal. Then I could figure out all this other stuff, right? I know that v sub x is just gonna be 16.5. Oh, I should have had, that should have been a sign, shouldn't it? Right, darn it. See what I did there, I made one little mistake, I made that as, so same argument, just should have been sine instead of cosine. Right, that should have been, that should have been, that should have been. Those all should have been sines. And so those should have been arc sines instead of arc cosines. Right? I caught that. So arc sine, and then whatever that gives me is going to be theta. And then when all is done, I could plug that in up here and find out what the horizontal component of the speed is, right? And if I want to know what displacement is, displacement horizontally is just going to be velocity times time. I know both of those then, right? And if I want to know how fast it's going when it hits the ground, that's just going to be the combination of those two final velocity vectors, right? I'm going to get a horizontal final velocity and a vertical final velocity that give me my overall final velocity, right? So I can use Pythagorean theorem. And if I want to know what this angle is, I can just do arctangent or something, right? Okay. Make sense? What is it asking for again?
As for angle, when the sun, or how many meters the sun hits the ground, and then the
Velocity. Okay, so all at once is just
yeah,
that then, right?
hits the ground with the speed of.
Speed of what? So that's going to be, if I combine the horizontal and vertical final velocities, right, using the Pythagorean theorem, okay? So I'm just kind of curious what the angle is. Let's find out. So what are we going to get here? So we get the arc sine of a bunch of stuff. Arc sine of the quantity. And we could even use, let's make a fraction, that template out of this. So alpha 1, so what's on the top? 4.9 times 6.11 squared minus 90.9. All divided by 16.5 times 6.11, close parentheses, and what do we get? 65.90 to two places, right? So that's the initial angle that it's launched at. Okay, that's theta. Okay? And then once you get that, everything else is kind of downhill from there. Make sense? Yeah, that's challenging.
So to find how many meters in basic fifth is, you use the Pythagorean theorem, but
We wouldn't need to. No, we wouldn't need to because that's a horizontal issue, right? So now we could go back and we could do something like this. We could say, okay, well, what is the horizontal velocity? We know theta. It's just 16.5 times the cosine of that angle, right? So the horizontal, so it's about 6.737, blah, blah, blah. I got it in my calculator right there, right? And how far does it go? Well, how long is it in the air times how fast is it moving horizontally, right? Horizontal speed times time. So that speed times the time of 6.11, I think it was. So it goes that far, 41.17 meters. So whatever our sig figs are, I can't remember how many sig figs we keep. I think it's 3, so it'd be 41.2 meters.
and then to find the velocity of when it hits the ground, the speed of what?
That's right here, right? So we got the horizontal velocity is that number. The vertical velocity is, our final vertical velocity is what? Well, we never actually calculated, but we could. Right now we know time. We know our initial velocity, so we could use, for example, we could use this equation number 2 and find the final vertical velocity, right? We could add that to our list right here. Right? And what's gonna give us? It's just gonna give us, our initial velocity plus acceleration times time, all stuff we know. Because now we can plug in a number for this, we know theta, right? See what I'm saying? What double dog dairy?
It's a lot.
It's a lot. That might be worthy of a triple dog dairy. I don't know. Although I am skipping protocol to go straight to the triple dog dare, evidently.
Yeah.